So up next, we have Jade telling us about vector programming. A fun thing, I just did a lecture on x86 in the undergrad compiler class. So I talked about, what the first vector extension in x86 was? MMX. Yeah, so I get to tell them, in the 90s, there was this exciting thing called multimedia and CDs. It's fun to do the trip down memory lane.
It was a whole 64 bits, so many.
It was also titanium, but we don't speak of that.
Anyway, still extremely important. You cannot exceed something like 25% of your peak throughput on your CPU if you don't bother using these things. Maybe even worse than that. So take it away, Jade. Tell us how we cannot have terribly wimpy software.
So my name's Jade. I work at HPE with Brad on Chapel. So if you weren't sick of Chapel, you're going to hear more Chapel. But I'm going to be talking specifically about vector programming kind of through a lens of Chapel. And why would you want vector programming? As was just said, you really can't properly use the machine unless you're doing vector programming. And part of that is compilers are great at optimizing code, but they don't necessarily understand your domain space. Vectorization is really more of an art than a science. Compilers can do a lot, and they can optimize very straightforward code. But when it gets into something more complex, like, say, parsing JSON, it really requires some imagination. And so SIMD-JSON is a vector library to parse JSON. And it is the fastest JSON parsing library. And it does this vectorization by completely changing the algorithm, how it's parsing that JSON. That's just not something a compiler can logically change into. You really need to write for vectorization. But one of the problems with this is portability. I can write some assembly code for SIMD programming, but that's great, and it's only going to work on one computer. And as long as it works on one computer, it's great. But if I'm writing production software, I want all of my users to be able to use it. I don't want to think about the hardware details. I don't want to be locked behind x86. I don't want to be locked behind using a 4-wide vector lane. I just want to write fast code. I don't want to think about these details. So for this, I'm going to give you a brief example. This is kind of the hello world of SIMD programming. I'm going to take two vectors, two arrays. I'm going to multiply one of them by a scalar, sum them together. There's my result. This is mostly straightforward C++ code. Don't worry, you don't need to understand every piece of code on the slides. There are portable vector libraries for C++. Two notable ones, Highway from Google, and the recently ratified C++ 26 standard. Both of these codes, they're pretty much line for line the exact same thing. It's just that one of them is using Highway as the library, and one of them is using the standard C++ library. But they do the exact same thing. And there's so many frameworks in many different languages. You can look at Rust, Mojo, Swift, pick your favorite language. To write this, they all have the same common pattern. You're going to iterate over your domain space, your index. You're going to skip for each vector lane. You'll load your two elements. You'll do your math. And then you'll store that result back out. Now, when writing a vector library for Chapel, I wanted to kind of challenge this status quo. So here is that same Saxby code written in Chapel. And you'll notice kind of the structure here is a little different. There's none of those more explicit loads. If I compare this to the non-hand vector coded version in Chapel, they look very, very similar. And the one thing I want to call out here is the actual computation, the core body of the loop, is the exact same. There is no explicit vector loads, no explicit vector stores. I can just write my computation, and a human looking at this loop can easily see what is being done, and they don't need to be worried about the details of how do my vectors load and everything else. So when writing this library, the key is I want to be able to write explicit vector code, and I want it to be fast, but I don't want to worry about all of the nitty-gritty details. And the two things that I'm going to focus on for this talk is portability. I want to be able to write it for multiple architectures. And I want it to seamlessly integrate with the language that I'm using, which is Chapel. This is something I think that some of the C++ libraries have done really well with templating. Other languages, they kind of seamlessly go into their library, into their language. And this is what makes a good SIMD library. It feels like you're just writing code in that language. So big thing is iteration. In Chapel, it's really common to see two kinds of loops. One is I iterate over my indices. So this is like a normal for loop in C or C++. And then I index into my array. Or I can just iterate over the array itself and let the compiler handle the actual indexing and accessing of my array elements. So the same thing should be true for vectors. I can iterate over the vectors, and I use an iterator to give me the proper indices that I want to use, and then I can explicitly do that load. But I should also be able to let the compiler, the language, the library, handle that for me, and I can just iterate over the array, and it gives me vectors that I can do math with. Similarly, I don't want to have to think about what hardware I'm running on. For the most part in this library, vector types map down to real hardware. So there's a certain set of vectors that you can compile to, and where possible, that will actually map down to a real register. If those registers don't exist, you can still write that explicit vector code. It just gets kind of simulated and duplicated for you. So a really great example of this is on ARM Neon. There's no two 56-bit registers, so you just get two 128-bit registers, and you do the same thing. Something that is really difficult for SIMD libraries is the ability to do shuffles and kind of rearrange your vector elements. This is something that is really hard to get portably done correctly because every architecture does things differently. They like to make things hard for programmers. So something that CVL does is it just provides a higher level set of shuffles, permutations, and then you can compose your operations from that. So if I take two vectors, for example, interleave lower and interleave upper, kind of rearrange these elements rather than allowing me to arbitrarily shuffle these. So I'm imposing a limitation on the programmer, but I'm giving them portability. Now, Chapel is a parallel language. This library should just work seamlessly with distributed languages, and it does. If you can't see the difference between these three codes, I'll call it out for you, but the exact same iterators work with distributed code, parallel code. So I can just write my Chapel code the same way I normally would, but I also can do explicit vectors. So as one kind of big example of all of this put together, I'm going to walk through this k-means clustering algorithm, which is vectorized. Again, don't try and understand every piece of code on this slide. What's important is kind of the general overview of the vectorization. So something I'll call out here, like this is using explicit vector indices rather than trying to do those automatic loads because I'm going to use that indice over and over and over again for more than just loading vectors. So I want to use those indices. I'm going to do a branchless update of my distance. So I'll compute the distance, and then I'll compute a minimum. And all of this is done in vectorized instructions, doing bit selection. I'm actually going to do my computation in a separate function. This function is fully generic, reusable vector code. So I can write this and use it anywhere else in my code, not just this one loop. And I can just write math. There's no vectors in that code, but it's all generically turned into vectorized math, including that lovely little square root. And the best part of all of this is of course, it is fast. You get great performance as you scale out. I will note that once you start to get to the 100 million points, you'll see that the performance is not quite as good as it was at the 10 million. At that point, you're starting to reach, memory bandwidth. At a certain point, the hardware does limit you. So that's this big example. In conclusion, being able to write good vector code in a language, you need to have good abstractions over the hardware. So this library gives a good balance between the portability and performance that you need to write good vector code. And you can express your computation directly, making it easier for humans and AIs to read. And you don't have to bury it in bookkeeping. The code is available on GitHub. If you want to go roast my code, feel free. And there is some future work that I would love to work on. If you want to know more, come ask me afterwards. And with that, does anyone have any questions?
Okay, let's take maybe 2 questions or so. Do a first one here.
Thank you. This is a nice project. One of the tasks you often have to perform while manually writing vector code is to maybe partially unroll and tile a loop. Do you have a nice abstraction for that?
So yes, but those unrollings are like, there are chapel abstractions to do that. You don't need that in the library. So there are some limited chapel abstractions to say, unroll this loop 2 times, 4 times, however many times you want. And essentially that just ties directly into LLVM. But that is kind of a chapel language feature that the library just gets to use and the library doesn't need to worry about.
Do we have any other questions? Oh, great. We got one back here.
Hi, great talk. I had, I guess, sort of a related question, but oftentimes when you're writing vectorized code, of course, you'll have like multiple parallel streams of work that are accumulating into different accumulators so that you can, keep multiple functional units busy. I guess I'm wondering if you have any sort of abstractions for dealing with that in sort of a portable way.
So yes and no. You kind of get these and I'll come back to this example here. The accumulator here is, and let me see if I can find it, new cluster ID and new min distance. And those are the accumulators for various operations that are happening in this loop. You don't need to do anything too special. It's just an array or in a vector. And so you just get whatever the vector is in your code. It's not any different than any normal vectorization code.
Okay, thanks. Let's give Jade another round of applause real quick.